In this video I want to introduce a quantity known as magnetization, and I want to introduce this idea in the context of an electromagnet. Okay, so we saw in the last video about the Bohr magneton that the hydrogen atom with its electron orbiting in a circle around the nucleus has a magnetic dipole moment that has to do with the angular momentum associated with the orbit of the electron. And that's just one example of the fact that charge in motion is the source of all magnetism. Okay, so an electromagnet also exemplifies the idea that charge in motion is the source of all magnetism. In this case, the charge in motion is the conventional current flowing in a wire. And I want you to use the right-hand rule and verify that this diagram has labeled the north and south correctly. So if you use the fingers of your right hand to mimic this coil of wire winding around and around in this direction, if your fingers wrap in the same direction as the wire, then doesn't your thumb point to the right? And so that indicates that this side of the solenoid is a north pole. So external to the solenoid, magnetic field lines seem to be coming away from this north. And external to it, they're coming into the south end. Internal to the solenoid within the magnet, right? This whole thing then acts like a magnet. Inside of it, the magnetic field lines continue on and go from south to north, wrap around on themselves, and continue to form complete loops. So there's a way you can make this electromagnet stronger. And all you have to do is wrap the solenoid around a core that's just made out of a big chunk of metal. Now, ideally, that core is made out of not paramagnetic, not diamagnetic, but rather ferromagnetic material. If you wrap the solenoid around ferromagnetic material, then you're going to increase the strength of the electromagnet when current flows through the wire. But let's work our way up to an understanding of ferromagnetic materials and start with paramagnetic. So I have a list here of values for paramagnetic and diamagnetic materials. So let's pick something like aluminum, right? Aluminum has this small numerical value that we'll get to in a bit, known as the magnetic susceptibility. But for now, let's just note that aluminum falls into the category of paramagnetic materials. So I can try to explain that if we focus on just one region, one chunk of this cylindrical core of aluminum. All right, so we're going to expand our view of that segment of the volume of this material. Now keep in mind that the magnetic field lines would be there whether the aluminum is there or not. Once a current flows in the wire, then we're going to have the same sort of magnetic fields that we have in the diagram above, right? The idea is that overall magnetism might increase because of the behavior of the atoms that make up the aluminum. So that's what I want to zoom in on here. Okay, so this is the same chunk of material. Now, aluminum is quite a bit different than hydrogen, right? It's got a lot more than just one proton in the nucleus and one electron in orbit. What makes it paramagnetic material is that the electrons that are orbiting the nucleus don't completely pair up. So in other words, the magnetic dipole moment for aluminum is definitely not zero. It has a magnetic dipole moment to it. Now, maybe that atom right there has a magnetic dipole moment that points this way. And maybe this atom of aluminum has a magnetic dipole moment that points this way. And maybe this one has a magnetic dipole moment that points that way, and this one points that way. So I'm just trying to say that they probably all point in random directions until the switch is closed and the current develops that flows through the solenoid and creates these field lines that we've pictured. And now what happens, as you know, is a magnetic field is able to exert a torque on a object with a magnetic dipole moment. The torque is the cross product of the dipole moment and the external magnetic field. So what happens, those aluminum atoms and their magnetic dipole moments align with the external field. So if the external field points to the right, then the dipole moments point mainly to the right and tend to align with the external field. Now the effect of that is that the new net magnetic field for our electromagnet is equal to, well, let's just say B naught is what the magnetic field would have been without wrapping the wires around the aluminum core. So the net magnetic field is whatever the original field would have been without the aluminum plus, well, okay, so here's where the quantity of magnetization comes in. So there's, this figure's not drawn to scale, right? If this chunk of aluminum is this large, the atoms that make it up are much smaller than this, right? We can't properly picture them. So there's a whole lot of them. And because they align, the magnetic field, the magnetic dipole moment of one of them adds with the magnetic dipole moment of another, which adds with the magnetic dipole moment. And there's thousands and thousands and millions and billions of these atoms whose magnetic dipoles align and add up. So what we can say is there's some overall net magnetic dipole moment. And if we divide the total magnetic dipole moment found by adding all the dipole moments together and then divide that by the total volume, right? We've got length, how about length times width times height? So if we divide the overall magnetic dipole moment by the volume, we get this quantity known as magnetization. So it's that magnetization that develops by having all of the atoms' dipole moments align that cause the new magnetic field or the net magnetic field of the electromagnet wound around an aluminum core to be a little bit larger than the original. But the units don't work out, right? This is in Teslas. This is in Teslas. And so I would have to add Teslas with Teslas. But let's check out the units here. You remember that the units for magnetic dipole moment, because magnetic dipole moment is the product of current and area, it has units of amps times square meters, and I'm dividing by volume, which has units of cubic meter. So magnetization has units of amps per meter, and an amp per meter is not a Tesla. So here we'd be adding Teslas with, okay, so there has to be a constant here, right? So let's think about what the units would have to be for that constant. B equals B naught plus some constant times magnetization. No, magnetic field is a vector, magnetization is a vector. So the constant here, what the heck is it? What could I multiply by amps per meter in order to get Teslas? Well, I suppose we could just reverse engineer it and say, if this were in Tesla times meters per amp, and then we multiplied that by an amp per meter, amps and meters would cancel and you'd be left with Tesla. So indeed, whatever constant we have here would have to have units of Tesla meters per amp, but I think you already know of a quantity that has units of Tesla meters per amp. In this unit, we introduced a quantity mu naught, known as the permeability of free space, and it's equal to 4 pi times 10 to the negative 7th, Tesla meters per amp. So in fact, that's the constant that goes in this equation. So by wrapping a solenoid around some metal core, its magnetic field goes up by a quantity equal to the permeability of free space multiplied by the magnetization of the material that the solenoid is wound around. Now, the magnetization of aluminum is really small, okay? So you're not going to get that great of an effect. Oh, and, boy, this is sad, isn't it? I suppose I should apologize here. We have mu being used in two different ways in this lesson. So you're going to see mu naught, and then you're going to see mu with a vector symbol on top of it. So here we have mu naught, and it's that quantity of 4 pi times 10 to the negative 7th Tesla meters per amp that we call the permeability of free space. And then we also have mu as a vector that represents magnetic dipole moment, and it has units of amps times square meters. So just take it in context and be careful. Indeed, it can be confusing to see mu used in two different ways in the same lesson. Okay, so what if we were to take that same solenoid and instead of wrapping it around aluminum, what if we wound it around, let's pick another material. What if we use something like copper? Well, when it comes to copper, the atoms of copper, if I try to draw vectors that represent their magnetic dipole moment, I can't, because the magnetic dipole moment for copper atoms is equal to 0. However, when the copper cylinder has a solenoid wound around it and current flows into that solenoid, the magnetic field lines appear, and the magnetic field lines induce a sort of magnetic dipole moment in the copper atoms. But the result, if the external magnetic field due to the winding of the solenoid points to the right, the induced magnetic dipole moments of the copper will point to the left. Now that's due to something known as Lenz's law, which governs the behavior of all magnetism that's induced. Lenz's law describes induced magnetism. Now I'm getting a little ahead of myself by saying that. That's actually the subject of Unit 4.3, which comes up next. So just for now, recognize that when it comes to materials like copper, which are diamagnetic instead of paramagnetic, the associated magnetic dipole moments point opposite the field, and so what you have is a decrease in the overall magnetic field. And so, gosh, you know what? There's another way we could say this, I guess, right? If the net magnetic field changes in comparison to the original magnetic field, we can say that the new magnetic field, by winding the solenoid around some metal core, is equal to some constant multiplied by the original magnetic field you would get when the solenoid is just filled with air and not wound around the metal. So this constant, we'll call it capital K subscript M, and that stands for the relative permeability of the material. Relative permeability has values that are pretty close to 1. So for most paramagnetic materials, the relative permeability is generally something like 1.00001 to as much as 1.003. So you can see that when your electromagnet is wound around materials like platinum or aluminum or even uranium, you're not going to get a very large increase in the magnetic field. Maybe it would be better to say how far these numbers venture from 1. So we can make a new quantity that might look like a capital X, but this is the Greek letter chi, and it stands for magnetic susceptibility. And we find the magnetic susceptibility just by taking the relative permeability and subtracting 1. So for example, aluminum, the one we referenced earlier, it has a relative permeability of 1.0000022. So if we go 1, 2, 3, 4, 5, then we could say that it has a susceptibility equal to 2.2 times 10 to the negative fifth. Oh, and by the way, what are the units for the relative permeability and the magnetic susceptibility? Well, if we go back to our equation here, the units for relative permeability, there are none. It's a dimensionless quantity, meaning it has no units at all. And you could see that, right? Because the original magnetic field is in Teslas, the new magnetic field is in Teslas, so K is just a numerical value, strictly speaking. And because susceptibility is just the relative permeability minus 1, it's also a dimensionless quantity. All right, so if we look back in the table, do we have that right? Yeah, aluminum has 2.2 times 10 to the negative fifth. Platinum, on the other hand, has a susceptibility of 26. So that means for platinum, its relative permeability is equal to 1.00026. So if we go 1, 2, 3, 4, 5 places over, that's why we say its susceptibility is equal to 26 times 10 to the negative fifth. All right. And because diamagnetic materials have induced magnetism that points opposite the external magnetic field, then the new magnetic field of your electromagnet is actually less than the original magnetic field, which means the relative permeability is a number that's a little bit less than 1 instead of being a little bit greater than 1, which means the magnetic susceptibilities are always negative for diamagnetic materials. And if you look at the list that I provided, sure enough, mercury and silver and carbon and lead all have negative susceptibilities. Temperature has an effect. Temperature affects paramagnetic materials. It makes the magnetization go down as the temperature goes up. And again, if we imagine a cube of some paramagnetic material, and we have these dipole moments that are momentarily aligned. Maybe we have an external magnetic field that points upward. So if the magnetic dipole moments of the atoms originally were randomly aligned, the external magnet would make the dipole moments line up in roughly in the same direction as the external field. But then as you add temperature, there's random vibrations, there's random molecular motion that increases with increasing temperature that tends to bring the orientation back into some sort of random alignment. However, temperature doesn't seem to have an effect on diamagnetic materials because they don't have a magnetic dipole moment to begin with. The last set of material I want to refer to are fall in the class of ferromagnetic. And in ferromagnetic materials, you have atoms that don't need an external magnetic field to align. They just start to align with each other. So for example, if this atom right here has a magnetic dipole moment, mu vector, pointing in that direction, then the nearby atom is influenced by the magnetic field of the first one, and so its magnetic field points almost in the same direction. And then the next nearest atom kind of agrees with these other ones, and the atoms all have a magnetic dipole moment that mostly points in the same direction, right? So within this region of the material, there seems to be some magnetism that in general has at least a common component that points upward. Now that's not to say that there's any guarantee that some neighboring section of this material has its atoms aligned the same way. They will be aligned in some way, so maybe in this segment of the material, all the atoms influence one another and have their magnetic dipole moments mainly pointing to the right. Okay, so regions of a material like this have a name. Wherever clusters of atoms join forces and align, we say that that represents a magnetic domain. And these magnetic domains contain more than just 1, 2, 3, 4, or 5 atoms. They have thousands, millions, billions of atoms perhaps that all align. So what happens is the magnetic dipole moment of this one and this one and this one, they all add together, and you can get incredibly large magnetization values. And so if the equation is right, if the net magnetic field of the material is equal to whatever external magnetic field influences it plus this constant multiplied by the magnetization, because the magnetization is so great, that means that the relative permeability is a very large value. In fact, the relative permeability for ferromagnetic materials isn't a number just like 1.000 something or other. The relative permeability tends to be a number like 1,000, right? You can have hundreds or thousands or maybe even magnetic susceptibilities as large as 10,000, which means we don't really need, did I say relative permeability? That means the magnetic susceptibility is roughly the same value, right? Because susceptibility is just relative permeability minus 1. So 10,000 minus 1 is also pretty much 10,000, meaning when it comes to ferromagnetic materials, the relative permeability is pretty much equal to the susceptibility. So we don't even so much speak of susceptibility in that case. So what happens when you apply an external magnetic field to materials like this? If there were an external magnetic field applied to this ferromagnetic material, then the domains line up. So let's draw this again. So if this is some chunk of ferromagnetic material and it's placed in an external magnetic field that points this way, then these clusters of the material that we refer to as domains, not only do the dipole moments align within a domain, but all the domains line up with the external field. So these make for very strong magnets, right? Which is why if you're going to make an electromagnet, it's best not to just stop with the solenoid winding of wire, but it would behoove you to get a chunk of metal and wind the wire around that, and then just make sure that this metal is ferromagnetic so that all of its domains line up and it becomes a very strong magnet, right? So the 3 types of material that would be best for that are iron, nickel, or cobalt. Steel generally has a large iron content to it, so any alloy that contains these types of metals is ferromagnetic and would make for a good core for your electromagnet. Now, permanent magnets and the core of an electromagnet should have different properties. See, a permanent magnet, once I get the domains to align, I'd like to freeze them in place so that they stay aligned, so that I can remove my external magnetic field and the material will still be magnetized due to the alignment of the domains. That would make for a good permanent magnet, like the sort of thing you might stick to your refrigerator to hold something in place. However, when it comes to an electromagnet, I want to magnetize this steel core or iron core when the current is flowing. But as soon as I turn that current off, I would like it if all the magnetic domains went back to a random orientation. So we can express how permanent magnets behave differently than the core of an electromagnet if we investigate something known as the hysteresis loop for the material. And I will spare that for our next video lesson, so stay tuned.